Welcome back, chemistry fans. Today, we are going to finish up pre-spring break topics. We're going to right now talk about the heat of reaction. Now, we've already seen the heat of reaction in our graphs, but now we've got to calculate it. And you're saying, well, we already calculated a delta H, and I agree, but that was just for one substance as it changed temperatures. Today, what we're going to do is we're actually going to see what happens when a reactant becomes a product, how that changes the amount of heat that is given off. So let me share my screen and we will get right into this. There are going to be three ways in which we must calculate our heat. So let's see if we can figure them out together. And it looks like I already have some fabulous writing on here. So let me. Okay, so now heat of reaction. Again, we have seen this before. If you are looking back at your heat of reaction graph, it makes sense that the heat of reaction would be present on it. It is the difference between the reactants and the products. Now, if this graph were going to become an endothermic, it's still delta H. What we need to be aware of is that when you're exothermic, that value is going to be negative. Whenever we are endothermic, that value is going to be positive. Okay, so before we get into this discussion, what we must understand is that all heat must be accounted for in these reactions. And so if we look at these heats here, what we will see is that they all conform to a budget. In other words, we as families probably need to be disciplined and make sure that all of the money coming into our household is not exceeding, is not being exceeded by what goes out. So in other words, you only get so much paycheck. You can't go into debt. You should not go into debt. That leads to hardships and difficult challenges, decisions later on in your life. So make sure, just as a public service announcement, that you are being generous and that you are saving. Everything else is up to your discretion, but I feel like those are some good advices from an old man who has your best interest at heart. If we think about chemistry, there is also something called a heat budget. And just like the Earth does not continue to get hotter and hotter and hotter like Venus does. In fact, we have the capability to absorb just enough of the sun's energy that it keeps us nice and temperate so that life can exist here on the Earth. Most of it reflects right back out into the world. And then there is a small portion of it that is stored, and we utilize that as organisms like we talked about last time. Now, how we're going to utilize this in chemistry is through the term enthalpy. I know that that's a fancy word, and it seems like it might be pronounced many different ways. Enthalpy, however you wish to pronounce it. It's the fancy word that talks about the heat budget that is in a chemical reaction. So in other words, all of the heat that is stored in a chemical reaction, some of it will be released, some of it will be converted into storage for the products. And we have to account for all of that and make it into a final heat of reaction. I do not want you to get confused because there's going to be two terms that we must utilize today. There is a heat of formation and there is a heat of reaction. The heat of formation is exactly as it sounds. It is how much heat it takes to make a substance. The heat of reaction is how much heat is given off during the process of a reaction. So their definitions and terms seem to coordinate quite well here on this. I will start with talking about the heat of formation. Now, what you should notice is that your substitute today, he has provided you with a heat of formation table. I believe it is yellow in color. And if you consult this, you will notice that there is a heat of formation value for every single compound that we would want to use throughout the school year. Important to note on this, there are several of these compounds which aren't. They are pure elements. And every time we run into one of these uncombined elements, you will notice that their heat of formation is 0. That's because you do not require additional heat to make an element. Elements are already made. So there is no heat of formation. You don't have to put things together. You just have to access it. It's already been made. So the heat of formation of all elements is equal to 0. But all the other ones, you notice whenever we form it, it looks like the majority, the vast majority, give off a little bit of heat, because once the two separate elements combine to one, they save energy. It's kind of like whenever you get married. You were in two households, now you're in one whenever you come together. So you save money that way. One of the benefits of bringing together households. All right. Now, how do we utilize the heat of formation in chemistry is through our friend, the mole map. Now, you're saying, I know the mole map. I've used the mole map. Let me refresh your memory. If you start with moles, it is a multiplication process to convert it to any of the other units. To go to grams, we multiply by formula mass. To go to volume, we multiply by 22.4. To go to atoms, we multiply by 6.02 times 10 to the 23rd. If we want to reverse that process, if we want to turn it into moles, well, what that means is you're going to divide by 22.4. So if we are going in, we are dividing. And if we are going out, we are multiplying. Now, what if I told you that the mole map was not finished? You'd say, well, that's sure fitting for the way the school year has gone. So that is going to be the scenario that we are presented with. You are going to learn right now that there is one missing box. There's a box on top, which we have not yet accounted for. So let's get that going right now. It is going to be heat. Specifically, it's going to be the heat of formation. I ran out of room there. Heat of formation. Now, how do we get to the heat of formation value, or what is the heat of formation value that we're going to utilize for the conversion processes? Well, that is going to be what we just looked at on that table. It's everything on that table that we saw, except for the compounds that are elements. They don't have a 0 value. So all we're going to do is we're going to multiply or divide, and it works the same way. If we're moving away from moles, we will multiply. And if we are moving towards moles, we will divide by the heat of formation. So it, in fact, is possible. And what we're going to do in an example here is we can go from grams, a given amount of grams, and find out how much heat is needed to make that material. So here's our first example. I have 25 grams of SO2. So let's take a look at the mole map at how this works. If I have 25 grams of SO2 and I want to convert it into heat, the process requires us to go through moles. Follow the blue arrow and it says we will divide. What will we divide by? The weight of SO2, which is 64. So I take 25 and I divide it by 64, the weight off the periodic table. Sulfur weighs 32. Each of the oxygens weighs 16. That's where that value comes from. So 25 divided by 64, that is equal to 0.39 moles. Now, we're not asked for moles, we're asked for heat of formation. So if we look at the subsequent information involved in this problem, it says that the heat of formation is 297 kilojoules. Remember, the unit of heat is kilojoules. So I will take my 0.39 and I will multiply it by 297 kilojoules negative. So 0.39 times 297 negative is a negative 116 kilojoules. That's how much heat it is required to make 25 grams of SO2. Okay, now that was the first way in which we can calculate a heat value. The second way today that we're going to learn is the heat of reaction. I must remind you that reactants are on the left, products are on the right. I also want to remind you, these are called coefficients. If there's not a value there, it's an unwritten 1. So don't forget about that task. Heat of reaction. So this is what we are going to be solving for this time. And to get this, remember, it is the difference between these values. So what we're going to do is we're going to come up with this scenario here. And I know that this is a lot, the heat of reaction. Focus in on the bottom down here. You're saying that's not much better, Mr. G. That's still a whole lot of information. Well, let me see if I can help you with it. This is our heat of reaction that we're solving for. Reaction, for whatever reason in chemistry, is going to be abbreviated as RXN. So this is our heat of reaction. The little zeros that you see up in the air, they're not degree symbols. What they are is reference to integrals. If you recall from your math, there is a time from 0 to infinity. So what we are doing here is they are establishing that we are starting at time equals 0. That's what that is up there. That's saying that at the starting point, how much heat do the products have? At the starting point, how much heat do the reactants have? That's what they're stating here. Now, these HFs, remember, those are our heat of formations. So we must use the heat of formation values to solve for the heat of reaction values. You may be noticing that there are N's in front. Those are the coefficients. Those are the little numbers that we referenced in the previous slide. So coefficients, again, those are the numbers that are in front that I have circled here, 2, 1, and 2. For whatever the reason, they chose to use N's because they match up with what we were doing previously. Number of moles is an N value. I have already told you about triangles. They are a symbol that means the change. And then the last symbol that you see here, that is a sigma. A sigma is a mathematical symbol that means sum. So putting this all together, this formula says the heat of reaction is equal to the sum of the products minus the reactants. That's the big picture. It's products minus reactants. And that's very, very similar whenever we had delta T, which was equal to T of the finish minus T of the start. Okay, so we're ready to start utilizing this formula for our second equation. So what we're going to do is we are going to take the products minus the reactants. So I'm going to take 3 times CO2 plus 4 times H2O minus 1 times C3H8 minus 5 times O2. There was an unwritten 1 up here is where that 1 comes from. Now I'm going to go and substitute in these heats of formation. They are given to you. You could look them up on your table. But what we must remember is that oxygen has no heat of formation. It was already formed, so it's 0. So instead, I'm just going to plug in now my value for the CO2, which is negative 394. I'm going to substitute in my water, which is 286. I'm going to subtract from that the C3H8, which is 104. I'm now just going to simplify. So 3 times 394 is negative 1182. $286 times 4, that is 1144. And 104 subtracting. Now bring all those values together. And what you get is negative 142 joules. The units are joules. You must pay attention to what the units are as to what your unit is in the answer. All right, that's the second method for us to calculate heat of reactions today. The third is going to involve us understanding that there are always 2 paths at least to your destination. So if I wanted to drive from school to Stafford, there are 2 ways you can do it. You can go up Interstate 95, or you could go up Highway Route 1. Both of them will get you to Stafford. One of them is shorter than the other path, and that's okay, but they both get you there at the same at the same destination, to the same destination. So in chemistry, I need you to see that there are two paths to get to the products. If I have reactants right here, I could go to the products quite directly, and that amount of heat would be given here. Or I could take a more indirect path. But guess what? If I take the sum of all of those individual steps, it will sum to be the exact 393.5. It does not matter how many steps it takes for me to get to the products, I will still have the same heat value. This is called Hess's law. So sometimes chemical reactions go slower, sometimes they go faster, but they always end up with the same amount of heat. So we are going to investigate that now with a mathematical process. And you're looking at this saying, oh my gosh, there's so much, it's so confusing. Here's what I need you to understand. These are called step reactions. These step reactions combine to make the total reaction. So what I need to do is sum together all of those heat values, and I get my total heat here. This is my heat of reaction. It didn't matter that I took all those small step reactions to get to it. If I could do it all in one step, it would be the exact same value. Our goal will be to solve for that heat value. So what we will notice, though, in this is that some of the materials in the step reactions, well, they didn't appear in the final reaction, in the total reaction. Notice there's no C's down below. That's because they canceled out. There's no oxygens down below or hydrogens down below. That's because they canceled out. Sorry, there's the other C. And there's no O2s down below, and that's because they canceled out. So we're going to learn how to do this. I've got one example problem, and then you are on, I've got two example problems, and then you are on your own. So I've got step reaction A, and I have step reaction B making the total down below. We've got to make sure that A and B are added together. And you're saying, okay, let's just add those together to get my answer. Well, that's not quite so simple. Notice in the final reaction, you don't have any oxygens, you don't have any carbon dioxides. So we've got to get rid of those. I also want you to notice that diamond is on the left side, but it's on the right side over here. So we must fix that. So what I will do is I will rewrite B. I will flip it. So I will have CO2 on the left. I will have C, that is a diamond, on the right, plus O2. And when I flip it, that now means that my math value, my heat value, becomes positive. It was negative, now it is positive. Now let's take a look. There's a CO2 on the right, there's a CO2 on the left. They canceled out. There's an oxygen on the left, there's an oxygen on the right. They canceled out. What I'm left with is what I need. Graphite on the left, diamond on the right. So now I take negative 393.5 plus 395.4. And what I end up with, my total heat is 1.9 kilojoules. Let's do one more example. This one is more complicated. Now, unfortunately, the total heat is written up above, so I'm going to move that down here to the bottom so it's a little bit easier for you to see how things are going to get canceled. So all I'm doing is rewriting the statement that is up above, because that is the total heat that's the total reaction that we need. We don't know what the total heat is. It didn't give it to us. I have 3-step reactions. We are going to use those 3-step reactions to cancel to figure out how to make it equal to the bottom. So let's start with the first one. I have NH3. I see it's on the left. That's where it needs to be, but it's only on the right in step B. So I'm going to rewrite this equation and put it on the correct side. So I've got 2 NH3s makes N2 plus 3 H2s. Because I reversed that, now this is going to become a positive. Now, notice this though. The amount is not correct. So what this means is I need to multiply the entire reaction by 2. If I multiply 2 times 2, I get 4. If I multiply this by 2, I get 2. And if I multiply that by 2, I get 6. Now, my ammonia, NH3, it is correct on the left side. So I know that step B is correct because I have one material that matches the total reaction. So that means that that is correct. So now let's move on to the next one. Well, oxygen is in 2 places. So that's not a wise choice because I don't know which one I should use to try and figure out. I can't do both of them at the same time. So let's skip the oxygen and let's move to the NO. The NO is on the correct side, but it's not with the correct amount. So what I'm going to do is I'm going to multiply this entire reaction by 2. In doing so, that will make 2 for the N2s, 2 for the O2s, and 4 for the NOs, which is what it needs to be in the total reaction. That means that this reaction is correct, except notice I multiplied by 2, then I need to multiply the heat by 2. The same thing down here, because I multiplied it by 2, I need to multiply my heat by 2. Now, the last step is our waters. There are 6 waters, but I only have 2 here. So that means I'm going to multiply this entire reaction by 3. That would give me 6 H2s. That would give me 3 O2s and 6 H2Os. Now everything's correct, but I do need to multiply my heat by 3. Now my oxygens. What you will notice magically, 2 plus 3 equals 5. Also, what you will start to notice is that I have N2. Oh, sorry, I canceled out this reaction. So I now have N2 on the right, 2 of them. That cancels with 2 N2s on the left. They are gone. They canceled out. The H2s, I have 6 H2s on the right. I have 6 H2s on the left. They canceled out. And that's the reason why they did not appear in my final reaction. So I have canceled out everything. I am left with everything that is in my final reaction. Now I just got to do the math. 2 times a negative 180.5 plus 2 times 91.8 minus 3 times 483.6. And what I end up with is negative, whoops, you can't see it, negative 1628.2. My units are in kilojoules. This is called Hess's law, and this is everything that I need for you to understand, comprehend, be able to utilize in today's lesson. This is it for us. We got one more topic when we get back from spring break, and then we'll have a quiz after that. So thank you very much for your attention. I know that this was challenging stuff. There's a homework practice problem for a couple of them, one for each of the different types for you to go and practice. Talk to you again soon. Farewell and happy spring break. Bye-bye.